Hello, my name is Zach Espinosa, and I'm an undergraduate at Stanford University studying computer science and applied physics. For Stanford's course in Natural Language Understanding, CS224U, I use deep learning to tackle the task of image captioning. In this short presentation, I explain the importance of image captioning, offer a brief overview of different approaches, describe my work, and present initial results. Automatically generating natural language captions based on the contents of an image is a particularly interesting and challenging task in artificial intelligence. A generated caption must not only recognize important subjects in the image and relationships between these subjects, but must also understand how to put ideas into words. Success in this task is not only useful in demonstrating the progress of natural language understanding, but has important practical applications such as image indexing and aiding the visually impaired. There exist two major paradigms in image captioning: the modern top-down approach and the classic bottom-up approach. Top-down implementations, like the one on the left by a team at Google, focus on creating an end-to-end product for machine translation. This paradigm uses a convolutional neural network, or encoder, to create an image embedding and a recurrent neural network to convert these embeddings into language. A slightly different approach is often described as bottom-up. This paradigm attempts to extract localized information from images and create relationships between regions of importance. Bottom-up approach often gives engineers more agency over the decisions in their model, but unfortunately does not create an end-to-end product. In this project, I implement a top-down model similar to Google NIC. I use a VGG16 convolutional neural network, aka an encoder, to encode images in a 4096 dimensional feature vector. I then use principal component analysis to reduce the dimensionality of these feature vectors to 512 and 256. This vector is then fed into a long, short-term memory recurrent neural network, which returns an English caption of no more than 20 words in length. During training, the decoder is given a human-generated caption along with its associated embedded image. Each caption is sandwiched between start and end delimiters. And during test time, the decoder is given the embedded image, and each subsequent word generated by the decoder is given to the next time step. I use the MS-COCO 2014 dataset containing 82,783 training images, 40,504 validation images, where each image is paired with 5 human-generated captions created by Amazon Turk workers. Due to different sized images, generating feature representations for images is computationally expensive and extremely redundant because it requires different sized, fully connected layers or image padding. In order to mitigate the computational costs of this project, I utilized the pre-processed MS-COCO dataset generated by Stanford's course, Convolutional Neural Networks for Vision Recognition. Moreover, this dataset conveniently pads captions with start and end delimiters. Every LSTM has a number of hyperparameters associated with it, including dropout, learning rate, and weight decay. After completing an extensive hyperparameter search, I found that my model performed fairly well. Moreover, while conducting a literature review, I found that previous works did not use pre-computed word embeddings to train their LSTM. For this reason, I thought that experimenting with glove word embeddings would offer the most to the community. Unsurprisingly, utilizing glove word embeddings improved results. This result is exciting as it suggests that perhaps there may be more room for improvement on the best models currently. As we can see from some of these results, there is certainly a lot of work to be done to improve this model's performance. Some next steps include using bidirectional LSTMs, different word embeddings, and exploring different encoder-decoder architectures.